Hi, so thank you very much. This is a talk about standardized scale-independent citation indicator. And what is the motivation? Every June, impact factors are announced, and every June we have the same pattern, that high impact factor journal ranks are always populated by small journals, publishing less than 1,000 papers a year, whereas large journals have got modest impact factors. So the impact factors are stratified in a way that small journals can score all the way from very small to very high impact factors. But as the journal size increases, then the larger journals occupy more and more central positions, average positions in the rankings. Another thing that we observe every year is that impact factors are highly volatile and due to single paper effects. For example, in 2017, 1 in 10 journals had their impact factor boosted by more than 50% by the top 3 cited papers. So clearly, journal size matters, and therefore high impact factor journals have an incentive to stay small to remain competitive in impact factor rankings. The question is, can we do anything to fix this? This is why the motivation behind this analysis. So the central limit theorem, which is a central theorem of statistics, allows us to quantify and perhaps find a way out of this situation. So suppose that you put together all the papers published over a 2-year window and cited over the year after. So this is a impact factor data set. And then you randomly select samples, random journals from this set. In this case, the sampling distribution is normally distributed, and therefore this inequality holds. The citation average is bounded by mu, the global citation average, plus or minus k sigma n, where sigma n is the sample standard deviation, and k can be 1, 2, 3. If it's 3, then for random journals, this inequality covers 99% of journals. The central limit theorem allows us to express this in terms of the global standard deviation, and that introduces the scale into the inequality. So you see there that the citation average is now bounded by quantities that depend inversely proportionally to the square root of the sample size, of the journal size. We can re-express this in this way, which starts to look like an uncertainty relation, and I call it the impact factor uncertainty relation, which says that the range of impact factor values shifted from the global mean is inversely proportional to 1 over square root of the journal size. And indeed, this is what we find. Here I show a case where I've randomly chosen journals from the physics condensed matter data set, and you see that for small sizes, impact factor citation averages can be very high, and they go down as the sample size increases, following the exact law predicted by the central limit theorem. And indeed, the central limit theorem, even though it applies to random journals, it actually can explain, so to speak, a large number of actual journals. For example, here we see that 3/4 out of all journals, 11,000 journals published by the Web of Science, they have impact factors that behave as if they were randomly selected, their papers, and they fall within the central limit theorem upper and lower limits. And the same holds if we look at the various subcategories. I show here 15. For example, in applied psychology, you see most dots fall within the limits and a few, of course, beyond. But generally, the trend is clearly that. So we can re-express the inequality we had before by putting everything together and form this quantity, the citation average minus the global average, divided by the standard deviation of the sample. If we do that, then we form this quantity, which I will call the phi index, which is, in words, it would be the distance of the impact factor from the mean normalized to the range of impact factors available, or the sample standard deviation. So immediately we see that defined this way, the phi index is standardized because it is analogous to the z-score in statistics. It can be used to describe citation averages in different fields, because you just plug in the mu and the sigma of the different fields, and then you get the rescaled citation average, the phi index. It remains to be seen whether it is scale independent. And it is a nice geometric interpretation. Assume here that we have two journals plotted their impact factor here, citation average versus the size. The journals are in locations A and B. Now, clearly A has got higher impact factor than B. But what I postulate here is that if points A and B are related in a certain way, then they are citation-wise equivalent. And what is the way for them to be related? It is that their distance from the global citation mean, rescaled by the range of impact factors available to them, should be equal. And which is to say, this length divided by this length should be equal to the equivalent for the point B. And if you do that, then you arrive at the equation of their phi indexes having to be equal. Now we can start calculating phi indexes for different journals, and we can consider all the papers published as belonging to one category. That will give us the sigma and the mu listed here, and these are the sigma and the mu's for different categories. And this is for categories in physics, from multidisciplinary to particles and fields. And the first test to run is the random journal test. And indeed, what we see here is that when we randomly form journals from these data sets, we see that although the impact factor, the citation average, indeed follows this 1 over square root of n behavior with scale, the phi index is largely independent of scale. Here we show actual phi index data in red versus the size of the journal for all 11,000 journals in the Web of Science journal citation reports. And for comparison, we also show in black impact factors. So a couple of things to note here is that phi index values can be high for small journals, medium and large journals, can also be small for medium, small and large journals. Some interesting rearrangements take place. For example, Living Reviews of Relativity and Advances in Physics goes down, Nature Reviews Drug Discovery goes up, as does Nature Physics, Nano Letters, PNAS, etc. And this is the ranking, the top 60 ranks by phi index. And we see here that the journal size is no longer seems to preclude journals from being listed in the top ranks. For example, we have journals that are quite large, say Nature Communications, its impact factor rank was 143, its phi index rank is number 10, and Gewandte Chemie from 148 to 13, etc. Here we show the phi index ranking of all 11,000 journals versus the impact factor ranking, and we see two regimes. This regime, this block, corresponds to positive phi index values for impact factor of both the global citation average, and this is negative phi index values. And very qualitatively, we looked at some extreme cases where the phi index ranking is much higher, much better than the impact factor ranking. And again, qualitatively, we feel that many of these make sense. For example, these journals are all pushed to high ranks. JAX, Nature Communications, like Gewandte Chemie, APS Nano, PNAS, etc. Now we go one step deeper. We say, what if we define the phi index not in a global field, as if all papers belong to the same field, but within the field of each journal? So all, say, economics journals are together, and we see if we recalculate phi indexes for these categories, how does the ranking of the journals in the category differ from if they were ranked based on the global phi index? And we see that for the most part, the rankings do not change much, which is encouraging, so there's some stability.
You have about 1 more minute.
Okay. Now let's go further. We see indeed that as we look at the in-field phi index rankings, we see that more and more subjects start to be introduced in the top ranks. As we can see here, there's more and more color available in the top 60 papers when we go from the phi index ranking to the in-field phi index ranking. So to conclude, we have explained how citation averages are scale dependent and volatile due to single papers. We use the central limit theorem to standardize citation averages and hence define the phi index, which is essentially the distance of the impact factor from the mean, rescaled by the standard deviation of the sample or the range of impact factors. The phi-index passes a random journal test. Phi-index rankings bring a wider mix of journal sizes in the top ranks, and in-field phi-index rankings bring a wider mix of subjects in the top ranks. Thank you.